Logic Circuits and Switching to your Laboratory, Project 1. So, good day everybody. My name is Jasper Espinosa, and this is my output for Project 1, which is entitled 7-Segment Display Decoder Circuit. For the statement of the problem, technology is very pervasive in our time today. We live in the age where information can now be transmitted and can easily be accessed through various technological platforms. Especially in our current situation today, information plays a vital role for the society. As part of the people at the back end of technology, our task is to make sure technological systems can accept, process, and present information accurately, specifically in computer systems where it can only operate in binary, which means it can only store and perform data calculations using zeros and ones. The processing part of the system must be well planned and designed to carry tasks accurately and to give users the adequate information they need. As electronics engineering students, we must equip ourselves with knowledge and experience in processing and presenting information accurately, thus the conduction of this project. The project is an application of learnings from logic functions and circuits, which is focused on the development and design of a 7-segment decoder circuit that will display 4-bit inputs, 4 bits binary input into its corresponding BCD, hexadecimal, and octal equivalent. For the scope and limitation of this project is primarily focused on displaying the decoded value from binary input into hexadecimal, octal, and BCD. Due to the current emergency situation, the actual implementation of this activity was not conducted. However, the project was designed and simulated virtually through NI Multisim software. For the components of this project, only transistor-transistor logic or TTL integrated circuits, specifically the 74LS family, was used, which are restricted to the common 2 input gates such as AND, OR, NAND, XOR, XNOR, and the inverter. The circuit design was powered with a regulated DC supply of 5 volts and structured implementation of UTP wire was observed. Interactive digital switches were utilized for the input, and 7 display segment is used to display the output. So for the short description of this project is composed of 4 channel input that will represent the 4 binary input. At the output, 3 7-segment display for hexadecimal, octal, and BCD is utilized to represent the corresponding 4-bit input. The project also used IC logic gates for processing the input and the output. For the system design and hardware specification, the components used in our project is 1. The 4 interactive digital switch, 3 7-segment display, which is a common cathode, the 74LS04, which is NOT gate integrated circuit, the 74LS00, a NAND gate integrated circuit, the 74LS08, AND gate integrated circuit, and 74LS32 OR gate IC. For the hardware and specification and pin configuration, for 7-segment display, as we can see in the picture, this is segment A, segment B, segment C, segment D, segment E, and segment G. And this is the particular pin diagram and its actual component. For the 74LS00 NAND gate integrated circuit, there are 4 NAND gates available in this integrated circuit. First gate, which is gate A, includes pins 1 and pin 2 as inputs and pin 3 as output. For gate B, pins 4 and 5 for inputs and output for pin 6. For the third gate, pins 9 and 10 as inputs with the output pin at pin 8. And lastly, at gate D, which have inputs at pin 12 and pin 13 with an output pin at pin 11. So pin 7 is for the ground and VCC is for the pin 14 or the supply voltage. For the 74LS08, which is AND gate integrated circuit, this component is composed of 4 AND gates, which is first gate, which is gate A, includes pins 1 and pins 2 as inputs, pin 3 as output. Gate B, pins 4 and 5 for input, and output is pin 6. For gate C, it is pins 9 and 10 as inputs with output at pin 8. And lastly, gate D, which have inputs at pin 12 and pin 13 with an output at pin 11. And pin 7 is for the ground and pin 14 for the supply voltage. For the 74LS32, OR gate integrated circuit, the number of gates is 4 OR gates in these components. The first gate, which is gate A, includes pins 1 and 2, as inputs and pin 3 as output. For gate B, or the second gate, which is 2A and 2B, pins 4 and 5 is for input and output for pin 6. For the third gate, consists of pins 9 and 10 as the input and output at pin 8. And at gate D, inputs at pin 12 and pin 13 with an output at pin 11. And for pin 7 is for the ground and pin 14 for the supply voltage or the VCC. For the 74LS04 or the NOT gate integrated circuit, this component is composed of 6 NOT gates, which is the first gate input pin 1 and output is pin 2. So there is one input only for this component and one output to its corresponding. The second gate have an input at pin 3 and with output at pin 4. So the third gate, pin 5, and the output is pin 6. Fourth gate, input at pin 9 and input at pin 9, the output at pin 8. And then for the fifth gate, input at pin 11 and output at pin 10. And lastly, the sixth gate, which is the input, is pin 13 and the output is pin 12. The same, pin 7 is for the ground and pin 14 for the supply voltage. For a general procedure of this experiment, first we have to determine the Boolean expression for each segment in the 7 display through Karnaugh map for hexadecimal, octal, and binary coded decimal. Second, we must map the Boolean expression into logic gate diagram. And number 3, implement the overall circuit design using IC logic gate. Number 4, connect the output for each segment to its corresponding segment pin into 7-segment display. Number 5, follow the correct pin configuration and supply 5 volts input voltage at VCC. And lastly, number 6, we have to observe structured wire implementation. First solutions is for the hexadecimal. This is the overall truth table for the hexadecimal. So starting from segment A, this is the segment A truth table. And through the use of Karnaugh map, we have obtained the Boolean expression for segment A. So the overall Boolean expression for segment A is not B and not D, or not B and not C, or not A and C, plus A and not D, plus not A and B and D, or A, not B, and C. So its corresponding logic diagram is here. So you can see. For segment B, segment D truth table, this is a truth table for segment B. And through the use of Karnaugh map, the Boolean expression obtained from segment B is not A and not B, plus not A and not C and not D, or not A, C, and D, plus not B and D, or A and not C and D. And its corresponding logic diagram is here. Segment B. For segment C, this is a truth table for segment C. And through the use of Karnaugh map, the Boolean expression obtained from segment C is not A and not C, or A and not B, or not A and D, plus or not C and D, or not A and B. And its corresponding logic gate diagram is here. For segment D truth table, this is a truth table for segment D, and through the use of Karnaugh map again, the Boolean expression obtained in segment D is A and not C, or not A and not B and not D, or not B and C and D, plus B and C and not D, plus B and not C and D. And its corresponding logic expression is here. For segment A truth table, this is a segment A truth table. And through the use of Karnaugh map again, the Boolean expression for segment E is not B and not D, or A and B, plus C and not D, plus or A and C. So this is the corresponding logic diagram for segment E. For segment F, this is segment F truth table. Through the use of Karnaugh map, the Boolean expression obtained in segment F is not C and D, not C and not D, or A and C plus B and not D, or A and not B, or not A, B, and C. And this corresponding logic diagram is here. For segment G through table, this is a segment G through table. Through the use of Carnap map, the Boolean expression obtained from segment G is not B and C, or C and not D, plus A and D, plus A and not B, plus not A, B, and not C. And the corresponding logic diagram is here. For the octal display, to make the design more economical and avoid adding unnecessary gates, all the Boolean expression and logic diagram decoding the binary input into octal is obtained by modifying each segment in hexadecimal. It was modified in such way that all the segments in the 7-segment display decoder for all octal will turn off when the binary input equivalent is more than 7. So if the input will be more than 7, the output for each segment will be turned off or 0. As you can see over here, for the input 1000, which is equals to 8, it is more than 7, so the output will return 0 for the rest of the remaining input. So from 8 to 15, the segment will turn off. For the Boolean expression, so the segment A from hexa is modified. So the Boolean expression that we obtain will be segment A from hexa and not A. And the corresponding logic diagram is here. So not A and segment A from hexadecimal, and will be output at segment A of octal. And this is true for all the segments. So we apply all of it at all the segments. Segment C, segment D, segment E, segment F, and segment G. For the binary coded decimal, to make the design more economical and avoid adding unnecessary gates, all the Boolean expression and logic diagram in decoding the binary input into BCD is obtained by modifying each segment to the hexadecimal. It was modified in such way that all the segments in the 7-segment display decoder for BCD will turn off when the binary input equivalent is more than 9. So as you can see in segment A, when the binary input is more than 9, in this case 1010, which is equal to 10, the segment will return 0, and this will be true for all the remaining inputs up to 15. It will return 0. So for the Boolean expression, segment A from hexa and A, NAND, B, or C. So this is the logic diagram. So segment A from hexa and the NAND of A from the B or C. And it will be segment A of BCD. And this will be true for all the segments, since this has the same function. If the input is more than 9 or it starts from 10, all the segments will turn off for the remaining input from 10 to 15. For the same circuit all throughout. And the only difference is this segment over here, which is obtained from its corresponding segment from hexa. And for segment G. So this is my final output for the 7-segment display decoder circuit, the project 1. So this is the overall implementation for the logic diagram obtained from each segment for the hexa, for the octal, and for the BCD. And it was implemented using integrated circuits logic kits. So in this design, I decided to use only 4 logic gates, which is the green one, it is the NOT gate, the 74LS04, the blue one, 74LS08, which is the AND gate, the 74LS32, or the OR gate, the red ones, and the 7 for LS00, the NAND key. And the VCC is powered 5 volts. And this is the above implementation for the segment A for hexa. The segment A for hexa, segment B, segment C, segment D, segment E, segment F, segment G. And as you can see, we have 4 input. It is the black A, the blue is C, green is B, and the red is D. And for the 7 segment display for octal, each segment for each hexa is modified accordingly so that it will carry the function for the octal, which will return the segment will return off. All the segment will turn off if the binary input equivalent is more than 7. And the same for BCD, each segment from hexa is modified accordingly so that it will carry the functionality that will turn off. All the segments will turn off if the binary input equivalent will be equals to 10. So if we simulate the project, run. So first, our input is 0, 0, 0, 0, which is equivalent to 0. So the output for hexa is 0, octal 0, and the BCD is 0. For the input 0, 0, 1, 0, 0, 1 is binary equivalent is 1. So the hexa will 1, the octal 1, and the BCD is also 1. The next input is 0, 0, 1, 0, which is equals to 2. So the hexa will return 2, the octal will display 2, and the BCD will display 2. And then next input is 0, 0, 1, 1, which is equals to 3. So the hexa will display 3, octal will also display 3, and the BCD will also display 3. Next input is 0, 1, 0, 0, which is equals to 4. So the hexa will be equal to 4, the octal 4, and the BCD is also 4. Next input is 0, 1, 0, 1, which is equivalent to 5. So the hexa will be 5, octal 5, and the BCD will decode 5. Next input is 0, 1, 1, 0, which is equals to 6. So the hexa is 66, the octal is 6, and the BCD is also 6. Next is 0, 1, 1, 1, or it's equivalent to 7. So the hexa is 7, octal is 7, and the BCD is 7. For the next input is 1, 0, 0, or equivalent to 8. So the hexa will return 8, and in this case, all the octal will turn off since the binary input equivalent is more than 7. So all the segments will turn off. And for the BCD, it will return 8. Next input is 1, 0, 0, 1, which is equivalent to 9. So hexa will return 9, the octal will remaining off, and the BCD will 9. For the next input, which is 1, 0, 1, 0, which is equivalent to 10. So hexa 10, the equivalent of hexa of 10 is letter A. For octal, it will turn off, and the BCD will turn off since the binary input equivalent is more than the 9. So it will turn off for the rest of the remaining input. And also the octal, it will turn off for the rest of the remaining input. Next input is 1, 0, 1, 1, which is equals to 11. So the hexa will display letter B. Next input is 12, which is 1, 1, 0, 0. So equivalent to 12 to hexa is letter C. So it will display C. So next input is 1101, which is equals to 13. And the equivalent hexa 13 is letter D. So the hexa will decode letter D. Next is 1110, which is equals to 14. And 14 for hexa is equivalent to E. And the display of the hexa will display letter E. And for the last 1111, so the last input, so equals to 15. So the hexa equivalent is letter F. And the octal and the BCD is off. And lastly, for the recommendations of this project, due to the current emergency situation today, the students were not able to develop their design in Actual. Therefore, it will be highly recommended to conduct this project in Actual to develop hands-on and manual skills. Also, in this project, the students can easily add circuits components. However, if their design will be reconstructed actually, addition of unnecessary IC logic gates can cause unnecessary expenses. Thus, it is highly recommended to simulate their design first, and they can make their design as economical as possible to lessen the expenses. Also, flexibility is required in the designing process because, or maybe, a certain type of gate will not be available in the market in the area, and you need to stick with limited type of logic gate integrated circuits. So in any case, if this project will be made with the same functionality, several ICs can be used, such as 74LS47, which is a 7-segment controller, is also recommended. In this way, we can minimize expenses, reduce the numbers of integrated circuits that will be used, save time in designing while carrying the same functionality. So that is all, and thank you very much.